pH for strong acids and strong bases. So remember, our strong acids are completely ionized, right? If I was to take HA for my strong acid, put it in water, every little bit of it is hydronium ions plus my conjugate base, right? It's completely ionized. So whatever my concentration of HA is my concentration of H3O plus, right? If I start out with 2 molar of this, I'm going to end up with 2 molar of my hydronium ion concentration, right? Because it's completely dissociated. That's not going to be true with weak acids because they exist in equilibrium. But for strong acids, because they're completely dissociated, my strong acid concentration is going to be my hydronium ion concentration. So if I gave you a 0.2 molar hydrochloric acid solution and wanted you to determine the pH, you would take the negative log of 0.2 molar because that acid concentration is my hydronium ion concentration. For bases, it's essentially the same thing. We're talking hydroxide instead of hydronium, but there is one little deal to watch out for, right? Every little bit of it is dissociated. So we could say that our strong base concentration is our hydroxide ion concentration. But do be careful. I'm going to put a big old red star on this, right? Some of my strong bases, right, I actually had 2 hydroxides. So watch out for those ones, right? If I had calcium hydroxide, I actually have 2. So when it dissociates, I end up with 2 calcium with a 2 plus charge and 2 hydroxide ions. So what that means for us, right? If I had 0.20 molar calcium hydroxide, I actually have 0.40 molar hydroxide ions. So the strong base concentration doesn't necessarily equal the hydroxide ion concentration if you have more than one hydroxide ion, right, per metal ion. So watch out for this big red star. Only when 1 metal per 1 hydroxide. When that's not the case, you then need to double it, right? Could be my hydroxide ion concentration equals 2 times my strong base concentration. I'm just going to use SB for strong base here. Is that making sense? Just pay attention. So if you have 1 hydroxide ion for every 1 base, then it's a 1-to-1 relationship. If you have, right, 2 hydroxide ions for every 1 base, then it's going to be a 2-to-1 relationship. You're going to have to multiply your concentration of strong base by 2 to get that hydroxide ion concentration. It's still, completely separated, right? Completely dissociated. It just happens to not be a 1-to-1 ratio. So let's look at some examples here. We're going to calculate the pH of a 0.102 molar chloric acid solution. So you do need to know that it's a strong acid. Right now we're only using strong acids, but next week we're going to calculate the pH for weak acids also. Once we do that, we have to be able to look at this and know that it's strong, because how we're going to calculate it is going to be different. So please, if you haven't learned those strong acids, do. Because this is a strong acid, I know that my hydronium ion concentration is also equal to that acid concentration, right? It's completely dissociated. So to figure out the pH, we're just going to take the negative log of that number. So I'm grabbing my calculator. And then for this one, I got 0.991. So again, watch the significant digits. I have 3 significant digits here, so I want 3 after the decimal point. Here, all of my digits are after the decimal point, so that's going to be my correct value for my pH. Another example for us. If the pH of a calcium hydroxide solution is 8.74, what is the concentration of calcium hydroxide? So this one's a little more involved, right? We're given the pH, and we know the pH is the negative log of my hydronium ion concentration. From that, I can figure out my hydroxide ion concentration, and then we can use the 1:2 ratio, right, to figure out my calcium hydroxide concentration, right? Calcium hydroxide, that falls into this one up here, right? For every 2 hydroxide ions, we have 1 calcium hydroxide. So once I determine the concentration of hydroxide ions, we're actually going to cut it in half to get the concentration of my base. So a few more steps. So again, pH is the negative log of hydronium ion concentration. We can do this one of 2 ways. I can use that pH plus POH, right? We can use that to figure out my POH, and then we can know that 10 raised to the negative of my POH is going to equal hydroxide ion. That tends to be my preferred method. The other way is to take 10 and raise it to the negative 8.74. That'll give you hydronium ion concentration. And then use, scrolling back up, I guess we're going a ways now, scrolling all the way back up, use our KW expression to get hydroxide. So essentially the 2 different ways that we did earlier. So I'm going to use the method that I wrote down here. So I'm going to take 14.00, I'm going to subtract 8.74, and I'm grabbing my calculator. I get 5.26, so that's my hydroxide ion concentration. Oops, sorry, that's my POH. And then to get my hydroxide ion concentration, we're going to take 10 and raise it to the negative of that. So when I type that into my calculator, I get 5.5 times 10 to the negative 6 molar. Again, watch your significant digits, right? This is only 2 significant digits. This 5 is coming from this exponent. That exponent doesn't count, so neither does that 5. So 2 sig figs, I want 2 significant digits in my answer. And then we're not done yet, right? This is my hydroxide ion concentration. The problem wants the concentration of my acid. So we would just cut it in half. And if you don't see that, you could set it up just using dimensional analysis, right? If I have 5.5 times 10 to the negative 6 molar OH, and if we were to write our reaction, right? There's 2 hydroxide ions for every 1. Since hydroxide's on the top, 2 moles of OH is going to go on the bottom, and then calcium hydroxide goes on the top. So we'll just take that number and divide it by 2. 2.7 times 10 to the negative 6 molar. Again, watch units and significant digits. I'm going to do another example. I just kind of want you to work through some on your own. So let's say if the concentration of a nitric acid solution is 2.74 times 10 to the negative 8th molar. What is its pH? And then also, is it acidic, basic, or neutral? So if the concentration of a nitric acid solution, so strong acid, is 2.74 times 10 to the negative 8th molar, what is its pH? And then is it acidic, basic, or neutral? So please hit pause, work through this problem on your own, answering both parts of the question, and then when you're ready, just hit play again. Alrighty, hopefully you guys did that. I know that the concentration of my strong acid, right, nitric acid is a strong acid, is equal to my concentration of hydronium ions. So that is 2.74 times 10 to the negative 8th molar. So to figure out the pH, it's just a matter of taking the negative log of that value. And I'm grabbing my calculator. And I get 7.562 as my answer. So again, watching significant digits, this has 3 significant digits. This 7 is not going to count, right? Only digits to the right of that decimal point for log values count. So this is my 3 significant digits. So 7.562. And then this is a basic solution. I actually did this on purpose. It's a strong acid, right? What that means is that it's completely ionized, right? In water, I have hydrogen ions, which attaches to water, so hydronium ions, plus nitrate ions. I don't have nitric acid. That's what it means to be a strong acid. Now, whether the solution is acidic, basic, or neutral, that depends on the relative hydronium to hydroxide ion concentration, right? If we just look at this original number, this is less than 1.0 times 10 to the negative 7th molar. It's basic. So even though it's a strong acid, I have such a small amount of that the dissociation, the ionization of water is actually making it a basic solution. So do be careful, right? Don't get acid and acidic mixed up. Don't get basic and a base mixed up, right? Whether our solution is acidic, basic, or neutral has to do with the relative hydronium to hydroxide ion concentration. So this is a solution that's made up of a strong acid and water, but the amount of acid I have is so small that my solution still comes out basic, right? This is larger than 7, right? Both of those things telling me that this is a basic solution. One more example for you to try on your own. If a solution has a pOH of 3.67, what is the hydronium ion concentration? And then is it acidic, basic, or neutral? So again, please try this one on your own. Hit pause, do the problem, and then hit play when you're ready to check. Alrighty, hopefully you guys did that. So we can answer the second part of the question first if we want. My pOH is less than 7, right? So that makes this a basic solution. We can finish the problem and then confirm that if we want. So my pOH, and we're trying to solve for hydronium. So this is one of the problems where you could have done it a couple different ways. I can subtract my pOH from 14.00 to get pH, and then take 10 and raise it to the negative of that value, which is how I'm likely to do it. The other way is I could figure out my hydroxide ion concentration by taking 10 and raising it to the negative 3.67, and then divide that answer into kW. Either way, we're going to get the same answer. Sometimes off a little bit with rounding and sig figs, but generally it's right on. So I'm going to do this one. I just think it's easier because I don't have to type in 1 times 10 to the negative 14th in my calculator. That's really the reason I do this. It's easier to just type in 14. So that's why I tend to do it this way. And since you get the same answer either way, do whichever is easier for you. So I get 10.33, and that's my pH, right? pH plus my pOH gives me 14.00. And then I'm just going to take 10 and raise it to the negative of my pH. And I get 4.7 times 10 to the negative 11th molar for my hydronium ion concentration. So hydronium ion concentration is less than 1 times 10 to the negative 3rd. My pH is 10.33, right? My pOH is less than 7. All of those things telling me that it is a basic solution. Just real quick, if you wanted to do it the other way, I know that my hydroxide ion concentration is 10 to the negative 3.67. So I'm just grabbing my calculator again. Don't forget the negative sign like I just did. Now I have 2 negative signs, sorry guys. 2.1 times 10 to the negative 4th molar, and then I would take kW, 1 times 10 to the negative 14th, divide it by my hydroxide ion concentration. Again, units don't work out, right? kW is my equilibrium constant. I'm not showing units. It actually has units of molar squared, so it actually does come out to be molar. Just be careful so you don't write the units incorrectly here. And I get, this time it does round a little bit different. I got 4.75, so 4.8 times 10 to the negative 11th molar. But either one of those work, whatever you're more comfortable with.